and do a quick video key for my recitation for my students for chapter 12 on conjugated systems. And so I'm just going to quickly go through this. The first one is explain what a conjugated system is, then explain why double bonds and conjugated systems are more stable than double bonds that are isolated. So a conjugated system is a series of overlapping p orbitals. I spelled overlapping wrong. Overlapping p orbitals that form a network of pi orbitals where electrons can be shared, where electrons are shared across a molecule, and they are responsible for resonance. I forgot to write they are responsible for, but they are responsible for resonance. They equal resonance. Okay, and the reason why that adds stability is pi orbitals are lower in energy than p orbitals because of the way that they share electrons. They distribute the electrons around the whole molecule, making the impact less on one area. Okay, so now draw pentadiene with the double bonds isolated from one another. So here's 1, 2, 3, 4, 5. Pentadiene, pentane, and then diene. So pentane means 5, diene means 2. So double bonds isolated from one another on the opposite sides. Double bonds in conjugation with one another. They're going to be alternating, but the thing I look for is a network of p orbitals that overlap each other and no gap between them. But you can also just think of alternating double bonds. And somebody called these infinity symbols, but I'm trying to draw the p orbitals there so that you can kind of visualize that the p orbitals, each one of these orbitals is sort of overlapping with one another to, instead of have these electrons concentrated, the electrons are shared across this whole system. So instead of it being like this, really, it's like the electrons are shared in those p orbitals across this whole system because they're able to move through these little p orbitals. And p orbitals are shaped like this, but they're not actually p orbitals. Once they start overlapping, they become pi orbitals, but those are harder to draw. So I just draw p orbitals. Okay, and identify which is more stable. I actually gave you the answer to that already. Conjugated bonds are more stable because the electrons are able to spread out. So that one is more stable. Okay, next question. Give the hybridization of each carbon atom. So this is sp2, and I know that because there's 3 electron domains. This one is also sp2, and I know that because there's 3 electron domains. And this one students sometimes struggle with, and that's okay. I want you to think right now, what do you think the orbital is and why? And I hope you pause the video and think about this before you let me answer it, because that is the best way for you to learn, is for you to try to think about it and give your best guess. All right. So I'm going to try to draw this out. If you think of your energy increasing, going up this y-axis, your energy increases as we go up that axis. We start with 3 p orbitals and an s orbital. And actually, if you think of having s and then px, py, and pz, if you have a hybrid orbital, all these are going to combine, and they actually lower in energy some to make sp3, and they make 4 sp3 orbitals. And the reason they're lower in energy is because you can think of these as 25% S and 75% P. So they have the energy, 25% of the energy of S and 75% of the energy of P. So they're about 3/4 of the way between these two. So between those two, a lone pair or a radical might choose to either be in a p orbital or an sp3 hybrid orbital. And clearly, a hybrid orbital would be better. So all the times before when you've had a radical like this, I would have told you to think of it as an electron domain area, and it'll go into hybridization. And so you might have said this is going to be sp3 hybrid. And that makes sense. But you didn't know about the potential at the time for conjugation. So if it's not an isolated radical and it could go into conjugation, that opens up a new orbital, a slightly lower in energy orbital called a pi orbital. So these are pi orbitals. They're lower in energy because conjugation lowers the energy from what a typical p orbital would be. Conjugation. I forgot how to spell that halfway through. So I'll just say conjugation. So if a lone pair could either be in a hybrid orbital or a pi orbital is lower in energy and therefore better. So for lone pairs and radicals, this is like a rule you can think of for lone pairs and radicals. Those count as an electron domain. An electron domain unless they can go into conjugation. And then they will go into conjugation if they can. Okay, so all that is a lot of background to say that this is an sp2 hybrid orbital as well, because this radical wants to go into conjugation. So now I'm going to show the p orbitals in vertical alignment. So I'm just going to draw them in green just because I can. Or sorry, in orange just because I can. I guess I could do it in green because that's what I drew them in earlier. So we gave the hybridization of each carbon atom. Oh, this one's sp3, I forgot to say. And now, for all the sp2 hybrid molecules, draw in a p orbital. So this is what a p orbital looks like. Okay, and then show the p orbitals in a vertical alignment, identify the bonding, non-bonding, and anti-bonding. So what I mean by that is drawing I should have written pi orbitals in the molecular orbital diagram. So our energy is increasing as we go up. And we have 3 pi orbitals because there's 3 p orbitals over here, and the number of pi orbitals is equal to the number of p orbitals. Basically, p orbitals overlap to form pi orbitals, and they form the same number. They form a bonding and anti-bonding. Okay, and then I think it's important to draw in the non-bonding line. So here's my non-bonding line. There is an orbital on the non-bonding line. This is a bonding orbital, and this is an anti-bonding orbital. And then I'm going to fill in the number of electrons. So there's 2 electrons that make up this pi bond and 1 right here on this radical. So we have 1, 2, 3 electrons. Then we have to, okay, so let's see. I showed the p orbitals in the vertical alignment, the molecular orbital diagram. I identified the bonding, non-bonding, and anti-bonding orbitals. I filled in the electrons so that I could identify the HOMO and the LUMO. So HOMO is the highest energy occupied molecular orbital. So highest energy means if we're looking at this graph, as the energy goes up, our higher energy is increasing as we go up. So the highest energy is this one that has electrons in it. That's what we mean by occupied. So this right here would be the HOMO. And then the LUMO is lowest unoccupied. So that means the lowest energy molecular orbital with nothing in it. So it usually is going to be the one right above the HOMO. So there's the LUMO. Okay, the HOMO-LUMO gap is the gap between those two. So this right here would be the HOMO-LUMO gap. And that determines how much light is absorbed. And that is often responsible for color. Okay, label each of the following molecules as having S, cis, S trans, or both. Then rank them in order of most stable to least stable. Okay, so S cis, I saw somebody in your class give this feedback. S cis, oh wait, hang on. Let's see. Actually, let me start over and I'll say, a lot of people ask me what the S stood for. S is sigma, so that's around a sigma bond. So traditionally, cis and trans, we would look at just on a double bond. You draw a line through a double bond. If these are on the opposite side, then it's trans. And if these are on the same side, then it's cis. So you could only identify cis or trans on an individual single bond. Well, now if we have two double bonds around a sigma bond, we can tell if they're cis or trans around the sigma. And so we say S cis or S trans. Now what's different is oftentimes they can rotate between sigma cis and sigma trans because of the sigma bond. So you can have sigma cis and sigma trans. So somebody gave me the tip, if you can't remember, draw a sigma or a diene in S cis as the C or S trans as the S, and that will help you remember it, and that helps me. So I thought that was really helpful. So, but another way you can look at the sigma bond and see, does it make sort of like a Z shape or does it make the C shape? So I would say this is S trans, and I saw a lot of people just writing cis or trans here, but make sure to write S, cis or S trans, because if you just wrote trans or cis on the test, it would be wrong. So I would say all three of these have that C shape, so all three of these are S cis, and all three, or the first two are S trans. And now we're trying to see which one are most stable or least stable. Well, as a whole, S cis and S trans are going to be, S trans is more stable than S cis. And within that, each individual double bond, cis, or I guess I can start with it, trans is more stable than cis. So looking at one here, we have a double bond that's trans and another double bond that's trans. If you drew a line through them, you can see the hydrogens are on opposite sides. So this is S trans, and it has two trans bonds. Now, the one here, number 2, has a cis bond. You can see these two hydrogens are on the same side of the double bond. So that means it has one cis bond, and then over here it has a trans bond. So between these two, 1 is more stable than 2. And we know that 2 is more stable than all of these S cis's because it's still S trans. Now we can do the same thing for each of these and see that this has a trans bond within S cis, and this also has a trans bond within S cis. So 2 trans bonds. That means it is the most stable S cis can possibly be. And then this one, if we look, it has a hydrogen here and here. So that's a cis bond. But over here, the hydrogens are on the opposite side. So it has 1 cis, 1 trans within S cis. So then this is the next most stable. And then this last one has 2 cis bonds. So it is the least stable. You can also look and see at like steric hindrance. which one is more or less hindered. That one I typically have students seem like it's a little bit more intuitive. Okay, for the reaction below, draw the mechanism of the reaction shown below. So I actually did this already. I'm going to draw in. I made a separate video about this if you're unsure, where I went kind of in detail about it. But since you can go check that out, I just posted it right before this video. I'm just going to draw in the answers here, and you can go see why they are what they are in that video if you're unsure. So this would be my two, after the hydrogen adds, you get these two resonance structures. So in reality, the structure is an average of these two together. And then the Br minus can attack either here or it can attack there. And so you get these two products. This is the 1,2 product, and this is the 1,4 product. So we drew the mechanism, and we drew the 1,2 and 1,4. Now I need to label which is the kinetic and which is thermodynamic. So thermodynamic is the more stable, and for alkenes, that means it's the more substituted. So that would be this one right here. More substituted alkene. So this one, I'll put it in, actually I'll do purple. This is the thermodynamic product. And then the easier one to form, but is less stable, is the 1,2. And this is the kinetic product. I accidentally cut off my bromine, so I'm going to redraw that. There we go. So kinetic product and thermodynamic product, I labeled each. How can I make the reaction produce either or? Well, I'm always going to get a mixture, but I'm going to guess around 50 degrees Celsius, it's going to start to favor the kinetic. And even probably around room temperature, honestly. Below room temperature, I would say it's going to, I'm going to say 0 degrees Celsius to favor the, oh wait, I'm sorry, I said this wrong. The thermodynamic is favored at higher temperatures for some reason. I was just thinking, I just said the wrong thing, but I knew what I was thinking. So if I want this one, I'm going to go higher temperatures. If I want this one, I'm going to go lower temperatures. Okay. All right. Now, draw the reaction mechanism for a basic Diels-Alder between 1,3-butadiene and ethene. Label the diene and dienophile. So this is the diene, and this is the dienophile. Now you'll notice I drew this in the S-cis. That's because it has to be an S-cis for Diels-Alder. Typically we would draw 1,3-butadiene like this, right? Butane is 4, so 1, 2, 3, 4 carbons. 1 and 3 each have an ene, so 1 and 3 have a double bond. So that's why we get 1,3-butadiene. Looks like this. But it's always easiest to draw Diels-Alder in this S-cis position. And then I like to number them, 1, 2, 3, 4, 5, and 6. So you can see kind of where each bond came from. And then I also like to highlight my bonds that are going to be in the action in colors so that you can see. So these electrons right here are going to make a new bond between 4 and 5. These are going to make a new bond between 1 and 6. And these are going to make a new pi bond between 2 and 3. So we always get a 6-membered ring for a Diels-Alder. So 1, 2, 3, 4, 5, and 6. And you get the new pi bond formed between 2 and 3. The bond that formed between 1 and 6 is this orange one here. That came from the pi bond between 5 and 6 previously, and the one that formed between 4 and 5 is the blue one that came from over there. So if you're feeling a little unsure about this, please go watch my video on Diels-Alder. We did this in class when I was feeling sick, and so we did it remotely, and I feel like that's not the best way to learn, but if you go watch this video on Diels-Alder, I think you're going to be in. Okay, hopefully that was helpful. I'll see y'all in class tomorrow.